There are some unusual phrases on the railway. Trains hunting has got to be one of the top ones. It isn't trains going rogue, but it is the train looking for something. So what is hunting? Hunting is a phenomenon where the wheels of the train move back and forth continually between the two rails. This weaving motion is not only uncomfortable for passengers, but can also cause damage to both the train and the track. So what causes this to happen? There are two instances where the train is sitting with the forces equally balanced between the two rails. First is on flat, straight track, and the second is when it's at equilibrium cant on a curve. In both these situations, the resultant force is directly into the sleepers. The resultant is the single force that results from two or more forces acting on an object. On flat track, there is no lateral force, so the resultant force is just the train mass, straight down. On the curve, there is the X or lateral force and the Y or vertical force from the train mass. The blue arrow shows the resultant force. For more on equilibrium cant and the forces acting on trains on a curve, check out the video linked at the top right now or in the description below. The issue with the resultant force acting directly into the sleepers becomes a problem when the wheel encounters any deviation, such as poor track geometry or a fault. This will cause it to react by not running perfectly parallel. The lack of any force pushing the train back towards either the left or the right rail leaves it to other factors to get the train back sitting centrally. This is where the conical nature of the wheels come into play. Train wheels are conical to help with keeping the train aligned with the track and also to help it steering round curves. Their radius increases the closer to the flange you get. When running parallel, both wheels run on the same area of the wheel, which therefore has the same radius. However, when the wheel deviates from parallel, causing a twist in the wheel set, an angle of attack is created. This in turn causes a disparity between the radii being used on each wheel. The wheel steering into the rail, marked A on our diagram, has its radius increased, while the other wheel, wheel B, has its radius decreased. Given the axle is fixed, so both wheels turn at the same speed, the only change can be in the distance each wheel covers. The wheel using the larger radius covers more distance, so overtakes the other wheel, turning it back towards the centre line. Ideally, this would be where the issue ended, with the wheels self-correcting to a central position. But there is nothing to stop the wheels passing through the centre line and the process happening again on the other side. A larger initial deviation will create a larger level of oscillation back and forth between the rails, and smaller ones create smaller oscillations. At lower speeds, this oscillation of the train is barely noticeable, covered by any other movement of the train. However, at higher speeds, the magnitude of the oscillation can increase, and was, at one time, a limiting factor in how fast trains could travel. The maths behind why this occurs gets very complicated and in-depth, but the root of the issue is that as the speed increases, the inertial forces come into play. This moves the behaviour away from a rigid system, where the movements are all proportional, to a system that behaves more like a weight or mass on a spring. In these systems, increases in energy increases the magnitude of the oscillations or movement to a larger extent and compounds. The train speed is the key source of energy for the system. It can cause the wheel flange to strike the rail in extreme cases after building up to that level of oscillation. So how is hunting prevented? On curves, the main way track engineers can combat hunting is by applying cant deficiency to the track. This is done by designing and installing the track with a value of cant less than the calculated equilibrium cant. By doing this, the resultant force direction is shifted towards the outer rail, which, among other benefits, keeps the train pushed towards the higher rail. This aids and speeds up self-correction should the train encounter anything that causes it to deviate, as it will always be pushed towards that higher rail by the overall resultant force. On straight track it's more tricky. Engineers have solved the issue, at least for speeds currently used, through changes to wheel design, notably in the angle of the conical shape, as well as changes to the train suspension. For example, HST class trains in the UK utilise a longer wheelbase, a flexible suspension system and lateral damping. All this reduced body instability, which in turn reduced the hunting issue up to over 125 miles per hour. So now you know what hunting is and some of the ways it can be prevented. I hope you've enjoyed this video. If you want to know more about railway engineering, a great place to start is with our Track Components Guide ebook that is available at the link in the description. If you want a little added extra, by signing up to our email list today at the link below, you'll get our free Guide to Cant ebook straight into your email inbox. Do drop any comments or queries below, hit that like button and subscribe so you don't miss a single video. Thank you.